Following the life cycle assessment LCA methodology, the environmental impact of different PV technologies can be obtained. Today, we shall show some comparative results from a specific case study. Two aspects will be covered. Firstly, a key set of impact indicators, and secondly, the environmental impact of both crystalline silicon and thin film PV technologies. Of course, the environmental impact of PV is minimal compared to conventional fossil fuels. However, by performing an LCA analysis, we can learn several critical aspects and how to minimize them. In the field of life cycle impact assessment, LCIA, numerous indicators are available for environmental impact assessments. For example, in commonly used EcoInvent database, there are originally a total of 692 product impact indicators, which could be reduced to 135 after applying some preliminary algorithm optimization. Making a decision based on so many indicators simultaneously is unfeasible. For this reason, different efforts have been devoted to reduce the number of indicators. The categories include midpoint indicators, endpoint indicators, and resource footprints regarding energy, water, land, and materials use. Different case studies could result in different key set adjustments. In this lecture, we take the example of one specific case study of the European Product Environmental Footprint Screening Lifecycle Assessment, which was reported in 2016. Be aware that the module efficiencies are out of date, and the use of these data will lead to less accurate results and interpretation. Still, the data could be used for comparing different technologies to each other. The observed most important impact categories are listed here, which will be discussed in the following slides. Here, a schematic of the analyzed PV system. The functional unit was defined as 1 kWh of direct current, DC electricity generated by a PV module. Full life cycle stages were considered, which include manufacturing, operation, and end-of-life phases. An optimally oriented PV panel installed in Europe was chosen. The degradation rate is assumed to be 0.7% per year, and the lifetime is 30 years. The production of the inverter was excluded and in the product system. Besides, different application scenarios were also considered. In our lecture, we only discuss the case of PV panels mounted on a slanted roof. For more detailed information, you can check the reference. 5 types of PV modules are addressed, including monocrystalline silicon, multicrystalline silicon, also called polycrystalline silicon, thin film silicon, cadmium telluride, and CIGS or CIS. Let's look at the results. For the impact category climate change, electricity production with cadmium telluride PV panels leads to the smallest environmental impact. The highest CO2 emissions occur for electricity generation by monocrystalline silicon PV panels. The difference between monocrystalline silicon and cadmium telluride PV panels mainly comes from the energy consumption to produce solar-grade silicon and silicon wafers, and the power plant mix in a manufacturing phase. The next factor is the mineral, fossil, and renewable resource depletion potential. The electricity production with CIS panels causes significantly higher impact with respect to other module types. This is mainly related to the consumption of indium, which is a scarce element, and its supply chain. Indium is also generally used in transparent conductive oxide layers of all thin film PV technologies. It is good to recall that in our previous course we discussed the development of high-performance crystalline silicon PV technologies with passivating contacts. Specifically for the silicon heterojunction case, the indium use is becoming more and more concerning since indium-based transparent conductive oxide is widely used in this type of solar cell. Therefore, we also need to pay attention to indium consumption in the silicon PV case when dealing with state-of-the-art and future technologies. The human toxicity includes cancer and non-cancer effects. In both cases, the systems with cadmium telluride PV panels cause the lowest impact among the 5 technologies, although it contains cadmium tellurium, which are toxic. For the other PV modules in this study, the results are comparable, except that the monocrystalline silicon case shows the highest non-cancer effects in human toxicity. Regarding the freshwater ecotoxicity, the calculated data from different PV technologies are comparable, but still the cadmium telluride case shows the lowest effect. The last 2 factors are particulate matter and acidification potential. These 2 indicators show a similar pattern. The electricity production with cadmium telluride PV panels leads to the lowest particulate matter and acidification potential impact, followed by the production of CIS PV panels. While the electricity production with monocrystalline silicon PV panels leads to much higher impact compared to cadmium telluride PV technology. To recap, in today's lecture, we spoke about 2 aspects. Firstly, there are numerous environmental impact indicators, among which it's necessary to pick up a key set for the analysis. Secondly, we discussed the comparative results from a European product environmental footprint screening life cycle assessment. 5 PV modules were discussed: monocrystalline silicon, multicrystalline silicon, thin film silicon, cadmium telluride, and CIS. Although the footprint is excellent for all technologies, we learned some critical aspects and to minimize this impact. The PV technologies were evaluated from different perspectives, including climate change, mineral, fossil and renewable source depletion potential, human toxicity, freshwater ecotoxicity, particulate matter and acidification potential. In all cases, cadmium telluride panels cause the least environmental impact. Of course, the impact is very low compared to the electricity generation by fossil fuels. In most cases, monocrystalline silicon panels give the highest impact potential. Exception is the fossil and renewable resource depletion potential, for which CIGS panels present the highest impact, mainly due to its Indian consumption. The environmental impact is caused by different materials and the corresponding process use. The materials used in traditional PV fields will be discussed in the next lecture. Different ways to further improve the environmental profile of PV will be discussed later in this course.